So, for the next hour, we're going to talk about wave particle scattering using the model of plane waves in GR and QED, and I'll tell you why you should care. We'll look at 2-point and 3-point functions, what kind of physics they contribute to, and then in the tutorial, we'll do some shock waves and some double copy stuff. Right. Okay. So. What I mean by a plane wave. To do that, I probably first need to tell you what my coordinates are. So let me do that over here. So for almost all of these lectures, I'm going to be working at light front coordinates. Sorry, Donal. He hates it. That's x plus, that's x minus, all right, in all directions. And I'm going to stick to 4 dimensions. Right, so there's also the transverse dimensions x and y. Okay, so x and y behave as normal, but t and z get replaced by x plus and x minus. Happy with that? Yeah, everyone's happy. So this is what the Minkowski metric looks like. Yeah, it's perp, dx. I'll use like perp just to label the 2 transverse directions. Yeah. Okay. All right. So then, given that, I can tell you what a plane wave is. This is minus QED first. X perp epsilon perp of x minus. So what is this? Draw that same space-time diagram. There's x plus. Ooh, I missed. There's x minus. Plane wave has 2 electric field components and 2 magnetic field components, which end up being the same as the electric ones. 2 functional degrees of freedom. Those fields point in the transverse directions, and is a function of this light-like cause x minus. Whenever you see an n, right, that n just projects onto the x minus direction. So what this looks like that there's some patch of space-time like that, which is filled with this electromagnetic field. It extends infinitely into the transverse directions. We're not going to worry about that. It's off, it's off, it's off. It wiggles a bit and then it turns back off again. Yeah, it's a wave. Literally, it's a wave. All right. Good. So in gravity, plane wave can be described like this. So that's Minkowski metric eta. That's 2 copies. Spoilers. And then you've got, using I and J to label the transverse directions. This guy H is a 2 by 2 symmetric traceless matrix. So that is 2 functional degrees of freedom again, just like in QED. Yeah. That's a solution of Maxwell's equations in vacuum. That's a solution of the Einstein's equations in vacuum. Okay. Very good. There are no scalar invariants that you can construct from this guy. There are no scalar invariants you can construct from this guy, but there is curvature, and these guys do couple to matter. So you can construct invariants once you throw something into these fields. The fact that you can't construct invariants just from the fields themselves is reflected in the fact that these guys do not spontaneously produce particles, right? If you think about, for example, FRW background, right, that will produce particles for you. Yeah, a strong electric field will produce particles. Plane waves don't. That's all right. And there is a nice well-defined X matrix in these backgrounds. So gravity, the situation looks exactly like this as well. And you've got some asymptotically free, genuinely free in region here. And you've got some free out region up there. It starts in the in region and goes to the out region, and it's all nice. It's a nice setup in which you study scattering. If you are not familiar with plane waves, all the classic papers are in 40, and comments on particle production and things like that, the existence of the S matrix. 44. Okay. Once again, why should you care? I know you all want to do Schwarzschild. I know you all want to do black holes. Right? There are other things to do as well. Right? One reason to care is the Penrose limit. Right? Basically says, in the neighborhood of a null geodesic, any metric looks like a plane wave metric. So that's why you should care. Some limit, everything is a plane wave. This is easy to understand in QED, right? Let's just forget gravity. Imagine I've got a particle going at super high energy, right? Goes through a field. It's super high energy, so it's going to barely get deflected. So eventually it's traveling along a null ray, right? It sees a null section of the field. Basically a plane wave. It sees something which depends on a light coordinate. Like that. That's all it is. Okay. Because these things are so simple, we have a very high degree of symmetry. You can get lots of nice analytic results, which is great for, you know, testing things and doing calculations beyond perturbation theory and beyond vacuum. And which I worked on for years, is that terrestrially, all of like the experimental results that come out of intense laser matter interactions are all based on using this plane wave model, extrapolated appropriately to more realistic conditions, right? So you really can get predictions out of this guy. Okay. All right. We have with the light transfer. Yes.
What sort of experiments with lasers do people do? Like, just an example.
Literally collide electrons with laser, watch them scatter, watch them produce pairs come out. So I mean, so send in an electron, it scatters. I'll talk about this a bit later on. Spits out radiation. You can measure radiation reaction, self-force effects and such. Or you can send in a photon into the laser, and that will interact with laser photons and pair create. It's also been done. And the helicity flip thing, where you send in photons and watch them change helicity state or scatter, which is a target. It's hard to see.
What are they trying to do with these experiments?
To see like the non-linear. So it's like it's in the non-linear and non-perturbative part of these guys. So we don't care about, if I expand this guy in perturbation theory, right? What is it? Like that comes to labor, it's Compton scattering. Who cares? Boring. Right? But the fact is you want to see the non-linear effect. So the all orders resummation of this is that guy. And it's those non-linear, non-perturbative effects that you want to see. Because basically QED has not been tested in that regime.
Precision QED.
Yeah, that's where it's getting to, towards precision QED. Unfortunately, a lot of this stuff is also done with plasma, and that's just not precise. Yeah. Okay, good. All right then. So let's start by thinking about 2 points. What do I need? Well, I need this, which is the propagator. But if I want the amplitude, then what I really want is the external legs, which are solutions of the Klein-Gordon equation or the Dirac equation in this background for QED. Start that. And I'm going to just do scalars. Right? So scalar QED. need the solution of that equation. Yeah. I'm going to write it down for you just so you can see the kind of structures that we're dealing with. That's simple. So imagine some particle coming in with momentum p. Right, and there's going to be an e to the I p dot x, because if I turn the field off, I get back to the field. And then there's another term, that's e to the I a dot x. I'll tell you what a is in just a second. Sorry. And then minus I, the integral x minus e from that to ea dot p minus e squared a squared over 2 n dot p. Well, that's all in the exponential. That's absolutely appalling. Poor management. There you go. Sorry about that. It's all in the exponential, right? What is all this stuff? So doing x minus this guy is pure. Right. So this thing A, which is appearing, is just the classical vector potential associated with the electric field, right? So this is the integral of the electric field. That n is the same vector n over there, so it's just projecting onto a particular momentum component. And I've got terms which are linear and quadratic in the exponent. In the exponents, this is manifestly all orders in the coupling from the get-go. This is the exact solution. And if I hand you a particular field profile, right? So I hand you an electric field, equivalently I hand you an A, then maybe you can do this integral in the exponent.
So it's integral with respect to what?
Second, sorry? Oh, apologies. Later on time. So A is a function of, maybe I put it in, x minus dot x. That's a function of later on time. That's a function of question?
You said if x goes to 0, you should get the free field.
No, if A goes to 0.
Oh, a, okay.
Yeah, so that term dies, that's all gone. It's an A as next. Yes. Similarly, if I take x to minus infinity, that term dies. That term dies by its definition. Right, so I just reduce the e to the IP back, so it becomes free. Yeah. All right. Yes. Can I kill this bit? We can see in that expression that all the deviations from the free bit are like EA. Yeah. So the interaction with this plane wave goes like EA. Let's make that dimensionless. So I'm going to divide it by m, electron mass. That's the only thing which makes sense. And then what is A really in terms of the electric field? It's the integral of the electric field. So it's like multiplying by some kind of length, dividing by a frequency. So the interaction with the field is typified by that quantity, which unfortunately is called A naught, which looks weird. It's not the 0th component of the potential, but yeah, sorry. So if that's like the typical electric field strength of the wave, and that is its typical frequency. Yeah, and the strength of interaction is just the charge mass ratio times the electric field over the frequency of the field. Yeah. Okay. So why am I telling you that? And what does it mean? Well, the point is, this thing A naught is of the order of 10 to 100. Right? If you think that I'm not going to take this opportunity to cite myself up the wazoo, you are. So that's the coupling of matter to the background, and it's larger than one. It's quite a bit larger than one, right? So you're not doing perturbation theory in powers of A naught. If you do, you can if you want, but you're not going to get an answer which bears any resemblance to experiment. Yeah. Let's look at the kind of, very roughly, the distinction between non-perturbative and perturbative. So A naught smaller than one and larger than one. If A naught, that quantity is one, right? Well, that is the same as saying I multiply, sorry. If I write the frequency as one of a wavelength, then what it says, there's my postdoc Carter coming in late. Shame. What does that say? The work done by the electric field over a laser wavelength is the rest mass of the electron. So when this guy A naught exceeds unity, right, you're accelerating particles to relativistic speeds over a single laser wavelength, right? So you're definitely doing relativistic. I don't want anyone to leave with the impression that, lasers, boring, piddly, dull science. It's not. It's cool. Obviously. What else could I do? Well, if I write M as one over the Compton wavelength, so lambda Compton, yeah, that's omega, the frequency of the laser, or if you put factors of H bar back in, the typical energy of the photons in the laser. All right. So the work done over a Compton wavelength exceeds the typical photon energy, which means you've got multi-photon effects. This is what manifests as nonlinear. Yeah. So you've got non-perturbative, relativistic, and nonlinear stuff going on in here, very roughly. This is why it's cool. All right. You can write down, let me just sketch it for you, the corresponding Gaussian gravity. It's a bit messier, unfortunately. Not quite as explicit, but the structures are not dissimilar. The solution of the wave equation, it's a bit like this. By using E. That E is not the same E. Let me write it down. All the labels I, A are all perpendicular. Minus I. Once again, this is all in the exponent. Right. So without going into too much detail, nothing gamma is some transverse metric, which is defined by the plane wave metric itself. This is a deformation tensor. This is some spibine. All defined by this 2x2 symmetric traceless guy, which appears in the metric plane wave. It's a bit less explicit than, so the actual expressions are much less explicit, but nevertheless, we've got the solution. Well, yes.
To like the electrical in your eyes.
Yes. Yeah, they are, yeah. So if you write down the linearized solution, it becomes much clearer. So then, you know, these guys are just integrals and derivatives of all H appearing in the metric. Exactly. It's not too dissimilar. You've got something quadratic in the transverse coordinates going on upstairs now, which is going to cause some headaches. Otherwise, it's a phase where the phase now depends non-trivially on light runtime x minus. If I think about that, if I refer to that as an addressed scalar field, right? So it's not just ETIP.x, it's ETIP.x dressed with all of this stuff. Then, of course, because in gravity, everything interacts with everything else. The graviton is also dressed. And I'm not going to write it down. It's a bit messier. More details. 47, 40, 44. And I think maybe Sonia will talk about this a little bit on Thursday. Yep. Thanks. Thanks. All right, good. So I give you the wave function, yeah.
What are the boundary conditions when you're solving this in the previous case?
The boundary conditions are the same, is that it reduces to e to the minus IP.x in the past. Very good. Yeah. Good. So actually, it's worth saying now, right? All these functions are good, like in the QED case, which I've annoyingly rubbed off the board, right? Everything goes back to the free solution in the past. In the future, it won't go back to quite that. So all these guys, the E, the sigma, the gamma, they'll all switch off in the past. They do not switch off in the future, but they do become equivalent to, well, they become really simple.
So there's also like an integral from minus infinity to x minus in the definition of those guys.
Yes. Okay. Yeah, exactly. So they're all integrated from the past forward. These things are found to be free in the past, and they are free in the future. Right? If I think about this wave as, you know, filling up some patch of space-time like that, and here there's no field, there's no curvature. Here there's no field, there's no curvature. So these solutions go back to free fields up here, but they don't look like free fields essentially because there's a memory effect, which we'll get onto in a second.
Here there are no assumptions on the coupling.
No,
Yeah. They're not doing this here.
no, exactly. So for exactly, so in the so if that's the metric, right, that is completely arbitrary. But I want to choose it so it looks a bit like, you know, something nice which turns on and turns off, right? And I'm not going to expand it in perturbation theory. Just put in a factor of kappa if you want. So, for example, those Veal binds, those phi binds, they satisfy an equation which looks roughly like that, with all the indices put back. So it's time-dependent harmonic oscillator. That's an x minus derivative. So there's very few cases where you can even solve this explicitly, but you know that the solutions obey certain properties. And blah, blah, that's but yeah, you just treat them as fixed functions throughout the calculation. All right.
So there is no A0 today in this case.
The AZ, let's see what's it going to look like. I started thinking about that and I didn't put in this notes because I wasn't convinced I was going to get it right. So if H is the thing appearing in the metric, I'm going to have to contract a momentum into it as well. And I think when you get stuck into it, there's also a dependence on impact parameter as well, or something like that. We might see it. Yeah, we'll see it. We will see it. So there is an analogous quantity which defines a strength interaction, but it's going to become dependent on impact parameter. Yeah, we'll get that. Anything else? No? Good. All right. So, what is this guy? Let's give that momentum P. Let's give that momentum P prime. And whether I'm doing 2D or gravity, doesn't matter. LSZ tells me that the 2-point amplitude will look like this. That's D2 x per dx plus e to the I p prime dot x id plus phi of x. Well, this guy is my incoming wave function from momentum p. Right, where did I pull this from? There's my wave. All this is the Klein-Gordon inner product evaluated on some surface up here where everything is free. This integral and this derivative, if you expand your field operator in free modes, the integral and derivative, all they do is pull out the annihilation operator. Yeah. So if you go to your textbook, the starting point for LSZ is to write something like this. A of, let's give it a label P. It is integral d cubed x e to the I p dot x dt phi, right? And then you go along and you convert that into a nice covariant expression with a d4x and blah, blah, blah. But that's where you start. Yeah? So all this does is just extract A from the free field. Now, because of the way this wave looks, right? It all depends on a null coordinate. If I look at what's happening at a fixed time, well, there's no sense in which the theory becomes free, right? I always intersect the wave. So I don't want to do that. Instead, what we do is look at what happens on a light-like surface up here. Yeah. And then basically you replace t with x plus, and your d cubed x becomes a dx plus dx plus. That's it. Yeah. There's nothing too mysterious about it.
This is the phi p field, which
We yeah, it's like this guy, for example. Yeah. So let's give it a little label P. You're absolutely right. So it's the guy which has incoming momentum P. What we're asking is, what is the amplitude to evolve to a state of momentum P prime in the future? Yeah. Okay. Okay, so give away like a calculator. What can I do with it? Well, I can calculate an observable, right? Let's look at the impulse or the change in momentum of this guy as it goes through the wave. So it's coming in, some momentum P. We'll get bent around a bit, and that's a terrible picture, Anton. My God. And then just some momentum P prime. Yeah. So I could so the change in the momentum is just the impulse. How do I calculate it? Well, I just take expectation value of the momentum operator, right? In that final state. What is that? The on shell integral of a P prime, and then I take prime multiplied by the probability. And of course, I should calculate this including wave packets, so on, so that it's all nice and regular. I'm not going to go into the details. Structure a little bit. So you can ask me what's really going on, what we're calculating. Boom, boom. Hat. Yeah. So I'm just sandwiching my momentum operator with a 2-point amplitude and its conjugate. My mod squared of A2. Yeah. We've got more diagrams like this later, so just kind of clear what's going on here. What I mean by this. Yeah. All right, very good. So skipping the calculation, but telling you the answer. This is what you get in QED. So E mu, it's E A mu at infinity plus N mu equal N to E A of infinity dot P minus E squared A squared infinity to N dot P. What's the expectation value? Two things to mention. First, it's not the same. So whatever this mess is, it's not the same as just P. Right? So the momentum that you get out is not the momentum that you put in. Secondly, I haven't said anything about H bar as a classical limit. So for this example and for this calculation, it turns out that the quantum value, the expectation value is H bar independent. So actually it matches the classical result. It's just because there's so much symmetry in plane waves, but it's a coincidence particularly. You can check yourselves. This guy's on shell. Here's all the memory stuff. Let's remind ourselves what is A, right? Well, imagine that my electric field looks like that. Electric field. Yeah. And A is the integral of that electric field. So it looks like that. So E might turn off, but A doesn't turn off. That's what the effect. You're just getting a kick from the particle. Sorry, you're getting a kick from the wave as you cross it. The fact that this is, well, its first contribution is linear in E, in the charge, might seem a little bit strange, because you think, okay, where am I going to get a term linear in the charge from if I'm doing bog standard perturbation theory? I could only come from a diagram like that, right? But that's zero. Everything is on shell, which is the case here because the plane wave is a vacuum solution, so it's made up of on shell. Yeah. Well, don't worry, you can sort it all out. It's in nice paper 21 by Facade. Facade. Yeah. There you go. Collaborators. Me and Doug. Yeah. So you can sort all that out. Okay. What is this thing? Well, if you go back to classical physics, right? And you solve the Lorentz force law in this background. So you solve an x double dot. The function of proper time tau is E F mu nu x of tau x dot mu tau. Right. So you solve that. Then what you find is if you take your solution and you calculate the momentum as the proper time goes to infinity, then you get that. Yeah. So what you're getting back is just the solution of like what is essentially the geodesic equation. Yeah. In electromagnetism. And I'm saying that because exactly the same story goes through in gravity. Without any changes. You calculate the 2 point. So this expression, which I ripped off the board, this expression, the expectation value of the momentum, your particle in the final state, exactly the same, right? You just check, swap out the 2 point amplitude for the one calculated in gravity. You do the integrals, and what falls out in the h bar to 0 limit is exactly what you would expect from solving the geodesic equation in the gravitational plane.
Gravity, there's an h bar to 0 limit in this case.
Yeah, there is actually. Yes, hang on. Am I misremembering? There is for the shock wave. Something subtle. I think there is an h bar to 0 limit in this case, I think. But ask again later and I might have changed my mind. So gravity, this is what you get. I can't write down the general solution like I can. So here I haven't specified what E is in any way, right? The electric fields, I haven't told you. All you need to know is that there is an A. Right, in gravity, because everything's a little bit less explicit, I can't write down the general solution for you. So what I'll do is pick a particular example. So let's imagine that we have an impulsive plane wave, which means that the functional dependence is a delta function. And then this thing H just becomes a constant matrix. Right? Still traceless. So still it's got two scalar degrees of freedom. In that case, what you get is in that case, and in that case only, a really simple map. I'm going to write it down here. It's exactly the same as the QED result, except wherever you see an A, which has some index, you replace that by, so wherever you see EA, becomes kappa over 2. Right, alarm bells should be ringing. You get a factor of n dot p, that's momentum, gravity, extra factor of momentum. And then you get that constant matrix, Hij, and then Bj, where B is the impact parameter. So what do I mean by impact parameter? So the metric is quadratic in the transverse coordinates. The wave functions were quadratic in the transverse coordinates, and there's some non-trivial transverse dependence there. So if you extrapolate this into the board where the transverse coordinates lives, let's just say there's some impact parameter. Yeah, there's some position where a classical particle would hit this wave. That's my impact parameter. Yeah. That's exactly the same expression, just swap out EA with its combination of kappa and momentum and impact. Yeah. For anything other than the impulsive case in gravity, the expressions are less explicit. But again, it matches exactly the solution to the geodesic equation.
Can I ask a question?
Yeah.
In the solution to the equation,
Yeah.
you have 3 objects that were made out of H, right?
Yes.
So
I knew which one this is, aren't you?
well, maybe not.
Good.
So the impulse, we're still gonna sandwich P mu nu with these 2 factors of the A. But then, so how can it be that the replacement is straightforward from A to H if in the solution to the equation you have to split them?
It's because of this impulsive limit. So in this limit, all of those 3 functions are expressed really simply in terms of H, this constant thing. It's just H
see.
maybe integrate, so multiplied by X minus or something like this. It's all very simple. So that's the only thing which falls out. It's purely in this impulsive case. Otherwise, it's messier, much messier. Yeah, good. Okay.
Wait, before you continue, so you mentioned that for QED, the fact that this coincides with the H bar to 0
Yeah.
was a coincidence.
Yes.
So this means that in your wave packets, so what are these wave packets then?
So what happens in the QED calculation is that the wave factors just sit there for the ride. They literally do nothing. The reason being that so the wave function that I'm plugging in are non-trivial functions of X minus, right? So X minus, which means I still have momentum conservation in 3 directions. All right. But if I'm doing one-to-one scattering, momentum conservation in 3 dimensions, is enough. It fixes everything. And what this means is that the wave packet literally just sits in front of everything. It factorizes out. You don't have to make any H-bar arguments or use Goldilocks relations or anything like this explicitly. It just sits there and eventually it integrates to one. It's gone.
But on the other hand, you also mentioned that, well, you're saying that this is the solution of the Lorentz force equation.
Yeah.
So this is not a coincidence, then it's a classical limit.
The quantum result and the classical result are the same. The plane waves in QED. The expectation value is the same. When we get onto, and this is particular to the 2-point amplitude. When we get onto the 3-point, then there's definite quantum stuff. I'll point out where it is. So the Volkov solution, sorry, I should have said, these wave functions are called Volkov solutions and they're semi-classical exact. So if you try and solve them with WKB, right, then your 1 over H bar term is the exact answer. You're done. All the high order stuff disappears, which is why. But it's very particular to this plane waves in Q. Good.
Yeah, with this memory term, how can I think of it in the usual self theorem? Sorry.
Excellent. So what is this? The X. So A is the integral, A of infinity is minus infinity of the electric field. That's the potential. What is that? That is the Fourier zero mode of the electric field. So it's the zero frequency. So it really is the soft stuff giving you this. Okay, so great. I can chuck a particle at a wave and I can scatter it and it'll bounce off and it'll get some momentum kick. Of course, what really happens is that I'll chuck it in, it'll bounce off, it'll get some momentum kick and it'll radiate. Well, let's think about what diagrams might describe the radiation. Particle going to a wave. Boom. And it's like, so let's have P coming in, P prime going out, and some K also going out. And again, maybe this is a photon, maybe it's a gravity. This is the first non-trivial contribution to radiation. It's order E, or order kappa, in this background field perturbation theory, yeah. But of course, it's order, all orders in the coupling to the background, yeah. That comes with an E or a kappa, but these double lines, they come with all orders of EA or kappa, yeah. What do we need to calculate this? I need wave functions, scalar wave function, the graviton wave function in principle. Yeah, I need the vertex. Vertex, we've already said, we just read it off from Lagrangian, it's the standard vertex. Yeah. It's just that the functions that you're plugging into it are now messy and horrible. So, just going to sketch structure of this amplitude. In gravity. No, actually, I need the space. So you'll start to see some of the complications doing calculations in background field. So the 3-point amplitude QD, scalar QD, looks like the following. You've got momentum conservation in 3 directions. Perpendicular plus directions. I'm going to give that outgoing guy a prime because otherwise it will just degenerate into looking like kappa. It's gone. Okay, so momentum conservation in 3 dimensions, and inside you've got your memory. It's still in there. Then you've got an integral. Light from time. And you've got something like the photon polarization dotted into, I need a symbol. P. Tell you what that is in a second. And then you've got an exponential up to this minus of k. What is all this stuff? Right. That capital P, that capital P is just the classical solution of the Lorentz force equation that we just talked about, right? Expressed in terms of the electric field and the potential A. Because of course, what this is describing, look at the diagram, right? If this double line is, the geodesics, and it's coming in, and we're looking at the radiation, which is spat off by a particle moving on a geodesic. That's it. So it's no surprise that that appears. Epsilon is just these epsilon. Of course, there's some spin on here, which I'm not worried about. This is photon polarization vector. This function, P, of course, depends on x minus. We can't do that integral. Right? You just dead in the water straight away. There's a couple of very special kinds of fields where you can do it, but for the most part, you can't. So you're kind of stuck. What else have we got? So the stuff to highlight is just that momentum conservation is only in 3D. You've got memory in there. This thing will generate all manner of special functions for you. So that's even at 3 points at tree level. What else? Yeah. The other thing which is in there, and this is not obvious, I appreciate it. If I put in all the factors of H bar, which I'm not going to do, right? There's a factor of H bar in there in Anton. And the fact that that is momentum minus the photon momentum, that's a recoil term. So radiation reaction is in here. I'll make this a bit more explicit, sure. Right? But it's in there. That's with the H bar. There is also, if you like, recoil. Okay. Vaguely similar for gravity. I'm going to put delta 3 in quotes there. It's not quite that because because memory effect is more complicated and it's a bit harder to write it down. But broadly speaking, it's a similar structure. And if I turn off the memory, I can do it. So yeah, thanks, Donald. Not good enough for a whiskey, sorry. Ah. Apart from like some subtle bits to do with memory, the rest of the structure is largely the same. What have we got? Now get, oh, sorry. Possibly unsurprisingly, the corresponding solution of the geodesic equation in gravity, except of course it rocks up twice. You get the graviton polarization, and this one's hard to draw. Of course, that also gets some kind of weird, funky notation because graviton wave function is a complicated function. Now, the graviton interacts with the background, so its momentum is changing all the time. Its polarization is changing all the time. So that's complicated, but otherwise, that's not screaming double copy at you. I don't know what is. And up in the exponent, again, you have something very similar. Integral plus minus. Now you've got the graviton momentum that is dressed, so it gets a funny bold label. There's P again, and underneath you've got the same structure. That's fine, and that's fine. The reason I'm not dressing these guys downstairs is because that momentum component is good. It's one of the guys appearing in the building. So not entirely dissimilar.
So can I have a question? What is the classical version of this process? So you have particle coming in and radiation reaction classically, or is this purely quantum?
No. The classical limit of this guy will give you radiation reaction. I'll get to it. I'll show you how. Yeah. Probably not as soon as I'd hoped. Okay, so we calculated an amplitude. Right? What kind of thing does it contribute to? Well, something is being radiated, right? So this amplitude must contribute to the radiated energy and momentum. So if I calculate the expectation value of the emitted photon or graviton momentum, our final state, that turns out to be equal to one shell measure, graviton or photon momentum, modulus 2 squared. Yeah. What is this? This is just in terms of diagrams. Amplitude, observable conjugate. Yeah. And this thing is, of course, this is quantum, right? This is a quantum object. It's got h bars all over the place, but you can expand an h bar and you can take the classical limit. Yeah, and of course you find agreement with classical calculations. So that's all good. But just to it's all fun and games. Find bit of a curiosity. The classical limit is fine, but when you get there, you find that you can't take the high energy limit of those results. Alternatively, you can't take the mass to 0. These things blow up. This has already been observed. Well, this is a property of radiative observables. Right. So for the 2-point function and the geodesic blah blah that we already talked about, I take the mass to 0. It's not a problem. All right. But for radiative observables, these things tend to blow up. This is already talked about in 53, 54, and many others for the full 2-body problem. But you know, they also appear in this wave particle scattering setup. Nicholas?
What are these 53 and 54?
Well,
when are they from?
One is Mao and collaborators. Herman, Parra Martinez, Ruff, and Zeng, 2021, and Vecchia, Hessenberg, Rousseau, Veneziano, 20.
That's Carlo.
Yeah, that's valid. Do you want to do this? Yeah. Oh, okay. What you find is these radiative observables have like power law mass singularities in QED and logarithmic mass singularities in gravity. The summary is this: so The reason that we look at this using the wave particle scattering setup is that you can get a very high orders in perturbation theory to see what's going on. So that's fine. You can do your classical limit. Right. Then if you try to go to the high energy limit, that doesn't work. Right, everything blows up. Alternatively, if you stay in the quantum theory, you can totally take the high energy limit. There's absolutely nothing wrong with scattering of massless particles in massless QED, QFT, whatever you want. That's absolutely fine. And then if you try and take the H bar goes to 0 limit of that guy, well, that doesn't work either. That explodes. Right. Yeah, so this is discussed in 51, written by Ricardo. Myself. So we looked at this in this wave particle scattering setup where you can actually do in QED, not in gravity, but in QED, you can do all orders classical calculations. So you can very cleanly take the high energy limit without knowing that you haven't missed anything. You've included radiation and recoil and radiation reaction and all of that. And no matter how many terms you add, no matter how high an order you go to in the classical theory, you still can't take the high energy limit. There's nothing which saves it, nothing which stops these mass singularities. The only thing which saves it is doing it quantum mechanically. So, one nice little thing you can get out of this, and boom, time.
And I still have a question
Yeah.
about the interpretation of this process because these stress propagators are sometimes hard to understand, right? So like in gravitational self force, you would kind of say, okay, I have radiated a graviton, it scatters on the background and it feeds into my massive particle and causes the particle to change its energy, angular momentum, and so on.
Yes.
So this is the kind of we are talking about here when you say radiation reaction, or
Exactly. So in this expression, I'm not looking at the scattered particles. Right? I'm looking at the radiated momentum. So I'm seeing the radiation.
Okay.
Maybe I'll eat into the tutorial time and show you how to get the show where the radiation reaction is. Because exactly as you say, right? This particle radiates and that affects its motion. I want to see that, I need to look at the motion. Right. I need to look at its final momentum that comes out.
somehow it's hidden in the, like, there would be like a blob there at the 3 point kind of.
It's hidden in this diagram and in another diagram as well.
Okay.
Yeah.
Well, what's this?
Yep.
Uh, you're saying that there is no way you can get even into the all of this. There is no way. Are you saying that because in GR you can set up?
I'm not saying anything about GR for
No, no, no. But let's say you without going through the quantum theory, you just do the computation in GR, and you in principle you can set up some scattering, very energetic. Are you saying that that is not predictive? Because
no.
you have to include quantum things.
Oh, maybe actually, yeah. All right.
We think that the classical prediction for very high energy scattering is not reliable.
No, I don't think I'm saying that. I think you probably get away with it. No,
I think it's related to the ultra-relativistic bound that also.
But exactly, but yeah, it is related to that. But are you saying that beyond that bound, GR is not predictive? It's not good. Like it's not a good theory.
Well, no, the bound Ricardo is talking about is just a bound about the post-Minkowskian approximation. So it doesn't work to first do small g and then take the velocity to infinity. But GR is well defined, of course, for velocity. Now for this, now for this is for the two-body scattering masses on the background, which is flat, which I understand better. Now this enhanced setup in which you have a strong field in the background is a bit less clear to me, I have to say. So I don't know.
Like in the UV, you're gonna find UV divergences, right? So in classical VR.
Would you?
Yeah, there is a issue of scales, right? As long as the shock waves have a size GE, which is much bigger than the impact parameter, E can also be very big, and you're still doing classical, so you shouldn't encounter the UV singularities that you worry about when
Yeah.
you do, because of which you say that GR is not a complete theory. That's what you have.
It's also like about the setup, right? So sometimes in classical GR you have exact solutions where you have two plane waves colliding and they fly about, and what is left looks nothing like Minkowski. So if you are doing this expansion, maybe you're just using the wrong base for expansion.
Yeah, so that's a good point. It should be said that, in this, even in the QED calculations, the background is still. No, it's not. No. Okay, no, I'm gonna let you guys talk about gravity. For QED, I'll say you can't do the high energy. So for classical electrodynamics, you can't do massless high energy. Definitely doesn't. Gravity, don't know. Yeah. Sorry, you've been waiting.
Right, I don't know if this limit makes sense, but can you have a scaling limit where we send M and H bar both to 0, but with some ratio, which makes sense?
Can't remember how the powers of H bar and M conspire. I think not. From what I remember, if I look at this limit, go from quantum to classical, I think there are terms something like this. Yeah, with appropriate field structures to get the dimensions right. Blah blah blah. So that if I fix that, then that's still going to be H. So I don't think so, from what I remember.
Maybe there's a missing arrow there, a diagonal.
That's actually what I was.
Find it. All right.
Yeah, I guess.
Yeah. Sorry.
Yeah, and, I think it's probably related to this question, but I mean, since taking the massless limit is taking your massive momentum to be massless momenta, and then you set up conservation of momentum, then you need a probability which will turn into the massless momentum within the Eigenergy limits,
Yeah, this might be. Yeah.
which is probably related to this H bar expansion.
We did look at this. There was nothing we could try to get it to. So you're exactly right. You could muck around with where the H bar dependence is in the momentum, but we couldn't find a prescription which would kill everything. All right, I guess I should pull Rafa.
No, doesn't matter the fact that you ignored selection and your mobility state does not change throughout the process.
So the QED calculation, so that comes from solving Lorentz Abraham Dirac equation, which does account for depletion and everything. It's all in there. So certainly in the QED case or electrodynamics case, that should be accounted for.